All right, so I've set up 4 problems that look really bizarre and unruly. And we're going to have to do some algebra to these in order to set up the point where we use L'Hopital's rule. Each one of them is an example of a particular kind of form that isn't easy to resolve. Let's take a look at the first one. As x approaches 0, you'll notice that this first piece looks like it's going to be 0. The second piece, when x approaches 0, 1 over x goes to infinity. So e to something really big goes to infinity. So this is really of the form 0 multiplied by infinity. And the question is, which one's going to win? Is 0 going to make it all collapse to 0? Or is infinity going to be so big that even 0 gets blown up to infinity? Or does it settle somewhere in between? The second one, both of these look very similar. This goes to infinity, this goes to infinity, but we're subtracting them. So we're looking at something that looks like infinity minus infinity. And so the question is one bigger than the other? Are they going to collapse? Are they going to cancel out? Or is one of them going to win? Is it going to go to plus infinity, to minus infinity, or to somewhere in between? We don't know. The third one is also really weird. As x blows up, 1 over x goes to 0. So the inside here just goes to 1. The outside, though, is blowing up to infinity. So this one is of the form 1 raised to the infinite power. But here's the thing. 1 to any power is just 1. But all of these are a little bit bigger than 1. So if you take something bigger than 1 and blow it up to infinity, it goes to infinity. So which one's going to win? Is this going to go up? Is it going to blow up? Is it going to stay at 1? Or is it going to stop somewhere in between? We don't know. The third one is also really weird because as x approaches 0, this goes to 0 and that goes to 0. But if you take a 0 and raise it to any power, it stays 0. But if you take any number that isn't 0 and raise it to the 0 power, you get 1. So which one is it going to be? Is the power being 0 forcing this to be 1? Or is the number being 0 forcing the whole thing to collapse to 0? We don't know. So each one of these can't be determined by just plugging in the limit. So we're going to have to do some algebra. And sometimes we're going to set up L'Hopital's rule. It will be obvious. Other times it won't be. So let's look at the very first one. When we're looking at something where one is going to 0 and the other one is going to infinity, the easiest way to make these obviously looking like L'Hopital's rule is to remember that 1 divided by 0 is infinity. So we're going to change it to look like infinity divided by 1 over 0. And that'll make this infinity over infinity, which we will be able to use L'Hopital's rule. So we're going to change it. And instead of taking x and multiplying e to the 1 over x by it, instead of multiplying by x, we're going to divide by the reciprocal of x, which is 1 over x. So this is exactly the same thing as this. The only difference is that now I made it look like a function divided by another function, both of which are going to infinity. Because as x goes to 0, this goes to infinity, and e to the infinity is also infinity. So now we are looking like something that is infinity over infinity, so we can use L'Hopital's rule. So this will be the limit as x goes to 0 from the left of the derivative of e to the negative 1 over x is going to be the derivative of 1 over x, which is negative 1 over x squared, multiplied by e to the 1 over x. And we divide by the derivative of 1 over x, which is negative 1 over x squared. And look, these just cancel out. The negative 1 over x squares knock each other out. And so we're left with the limit as x goes to 0 from the right of e to the 1 over x. And this is just going to blow up to infinity because when you plug in something really big into e, it goes to infinity. So in this particular case, e to the 1 over x won the race. Super satisfying, super nice to actually get this limit. Let's look at the second one. We're looking at the limit as x goes to infinity of the natural log of x plus 1 minus the natural log of x. Now, for this one, we could try to make it look like something like infinity over infinity by factoring out a piece and trying to see if we could divide. But here we actually have laws of logarithms that give us a way to actually combine these. This does become the limit as x goes to infinity of the natural log of the fraction, x plus 1 over x. And now, as x goes to infinity, the inside looks like x plus 1 over x. Well, we could use that particular limit and see what happens. And so this will actually be the natural log of the limit as x goes to infinity of x plus 1 over x. Now, to go from outside to inside, you can only do this if your function itself is continuous, and in this case it is. Now, this right here is of the form infinity over infinity, so we can use L'Hopital's rule to get actually what it'll be. So this will be the natural log of the limit as x goes to infinity. The derivative of x plus 1 is 1, and the derivative of x is 1. And so we just get 1 over 1, which is the natural log of 1, which is 0. So in this case, the two infinities go to infinity at the same speed. We'll have infinity minus infinity does in fact give us 0. Not guaranteed. Sometimes one of the infinities is actually bigger. So that gives us a good glimpse of the first two. The last two are similar. One looks like 1 to the infinity, the other 0 to infinity. And they both rely on a trick that uses the laws of logarithms. So let me erase our two examples here. And let me tell you what this trick is. The two properties we're going to use is that e to the natural log of x is x. So if you have an expression, you don't change it if you plug it into e and natural log because they're inverse function. And the second property we're going to use is that the natural log of a number to a power is just b times the natural log of that number. So this is undoing powers, just brings them out front for natural logs. With these together, we're going to handle both of these expressions. So let's start with the first one. Let's look at the limit as x goes to infinity of 1 plus 1 over x to the 2x. The issue here is this power needs to come down so that we can actually look at our expression and try to do something that involves L'Hopital's rule. So to do that, we're going to plug this entire expression into e to the natural log of x. So we're going to do e, first limit. We're doing the limit as x goes to infinity of e to the natural log of 1 plus 1 over x to the 2x. Now, all of this is inside the natural log, which means in this expression, my a is just 1 plus 1 over x. My b is the 2x. So this 2x is going to come out on front. So this will be the limit as x goes to infinity of e to the 2x times the natural log of 1 plus 1 over x. And now we can see that we can change this x here to be dividing this as 1 over x, because then we'll have something that looks like natural log of 1 is 0. And then when we divide by 1 over x, we'll also be going to 0. And so we'll make that piece in there look like 0 over 0. So this will be the limit as x goes to infinity of e to the 2 times the natural log of 1 plus 1 over x over 1 over x. So I took this x here and divided by its reciprocal 1 over x. Now for this piece, this I can use L'Hopital's rule on, because this looks like the natural log of 1 divided by 0. Natural log of 1 is 0, so this is of the form 0 divided by 0. So the limit as x goes to infinity, let's just do this upper piece here. The natural log of 1 plus 1 over x over 1 over x. By L'Hopital's rule, this is going to be the derivative of the top part, which is going to be negative 1 over x squared times 1 over 1 plus 1 over x, divided by the derivative of the bottom, which is negative 1 over x squared, and this will be the limit as x goes to infinity. The negative 1 over 1 squared cancel, and we're just left with the limit as x goes to infinity of 1 over 1 plus 1 over x. As x gets really big, 1 over x goes to 0, and so this collapses to 1. So this entire piece becomes 1, which means that this piece that's inside my parentheses goes to 1, and I'm left with e squared. E squared is my limit, so this entire thing becomes just e squared. So this gives us a way of doing really, really weird limits, even when you have an expression that looks like 1 raised to the infinity power. Let's take a look at the last one, which uses the same trick. We're going to look at the limit as x goes from 0 to the right of 2 to the x to the x power. And we're just going to plug it into e to the natural log of itself. So this will be the limit as x goes to 0 plus of e to the natural log of 2x to the x. And once again, x can come out in front. This becomes the limit as x goes to 0 plus of e to the x times the natural log of 2x. And now this looks like 0 times infinity. So 0 times infinity, we're not, again, sure who's going to win. And we don't want it to be 0 times infinity. We want it to be, we want a division, right? We want infinity divided by infinity. So to do that, we're going to change this x by dividing it by 1 over x, just like last time. So this will be the limit. X approaches 0 from the right, e to the natural log of 2x divided by 1 over x. And once again, we can use L'Hopital's rule. This becomes the limit as x goes to 0 from the right. E, the derivative of the natural log of 2x is actually just 1 over x, because the 2 cancels with the 2 here. So we'd have a 2 that comes out front, but that cancels with the 2 on the bottom, so it just becomes 1 over x. And on the bottom, the derivative of 1 over x is negative 1 over x squared. This is very similar to one of the first ones we did. The negative 1 over x squared flips, and so we're multiplying by x squared. And so we get the limit as x goes to 0 from the right of e to the negative x squared over x, which is just e to the negative x, which is going to be as x goes to 0, this is going to go to 0, which will just give us 1. And so the limit as x goes to 0 from the right of 2x to the x cancels down to 1. So that's it for today. Or at least that's it for using L'Hopital's rule. The third lesson is actually going to go back to integration. We're going to learn how do we find integrals when we have limits that come into play. So these are going to be called improper integrals, and I'll see you there.